Today, in this lecture, I'm going to tell you why it is necessary to think of ADS CFT as a quantum error correcting code. And in tomorrow's lectures, depending on progress today, I will also be talking about tensor network toy models and perhaps a little bit about bulk reconstruction in the entanglement wedge. So for today, the story goes back to some puzzling features of ADS CFT. So let me first review ADS CFT and these puzzling features, features of ADS CFT. So as we all know, ADS CFT is an exact duality between two different theories. One is quantum gravity in ADS space, and the other is conformal field theory on the boundary of ADS. What this means is there are several ways to interpret this duality. The first is that the partition function of the two sides are the same. And we can include sources, include boundary conditions. There's no mystery about this equality. On the other hand, we can also interpret this as a statement about states and operators in these two theories. It means that we can map states and operators from one side to the other side. And there's an exact one-to-one map between the two sides. So in particular, let's be concrete. This is a statement about a dictionary. So this is a picture of ADS. The inside is ADS. And we can have operators, phi, for example, at the center of ADS at some time. The metric of anti-de Sitter space can be written in some coordinate like this. So in this notation, D is always the boundary dimension. D plus 1 is the bulk dimension. And in the bulk, we have the T coordinate, the radial R coordinate, and the spherical coordinate in D minus 1 dimensions. The boundary has T and these spherical coordinates. So the dictionary, we know a little bit about the dictionary. So in particular, for example, we can map operators from the bulk to the boundary. If we take a bulk operator like this phi, we can take the boundary limit, and we also need to extract the right boundary limit by putting r to the delta there. And this gives a boundary operator O. So delta is related to the mass of the bulk field by some relation. And just to be sure about the notation here is X stands for a collection of the boundary coordinate, T and omega, the spherical coordinate. And I will sometimes also use little x to denote the collection of all bulk coordinate. That means R and capital X. So this is a very precise statement. It's an operator equation, and we can use it for many things. In particular, we can use this to calculate endpoint function of boundary operators in the CFT by calculating the corresponding bulk endpoint function and taking this limit. This turns, for example, complicated, strongly coupled endpoint function calculation on the boundary into a simpler, weakly coupled computation in the bulk. This is only part of the dictionary. We should ask how to map operators from the other, how to back away from the limit. So what is a bulk operator without taking the boundary limit? What is the bulk operator in terms of the CFT data? So the question is, what is phi itself? It should be some non-local operator in the CFT. So it's some smeared operator that we can write down in principle, and we like to be more concrete. So first, if we try to think about this operator in the CFT, we will run into a puzzle. I'll call this puzzle the radial commutativity puzzle. The statement is, let's consider first normal quantum field theory without gravity. In a normal quantum field theory, we have causality, and the causality means we cannot instantaneously influence physics space-like separated to where we are. And causality is enforced by what we call locality. Which is the statement that if we take any two operators, as long as they're space-like, then they commute. So this is a fundamental statement about the structure of operators in a quantum field theory. This is an operator statement. We might expect this to hold also in the bulk in the ADS-CFT correspondence. The reason is the bulk is very well described by quantum field theory weakly coupled to gravity, and there we can also imagine doing experiments, and it would be very hard to violate causality. So let's say that this relation is expected in the bulk. What that means is we have a phi of, let's say, little x, and we have O, and for simplicity, let's put them on the same time slice. So I'm going to draw a time slice, and they are on the same time slice. Let me call this O of y. So the statement is we might expect these operators commute. When they are on the same time slice. In thinking about this equality, we should think of phi as being defined through the ADS-CFT dictionary to be some non-local operator in the CFT. And then this is a statement in the CFT. So we have a CFT, complicated CFT operator, and we have a local operator in the CFT. And the statement is they commute. You might think this is very natural, but this is actually impossible. It is impossible because it contradicts the so-called Timeslice Axiom satisfied by any quantum field theory. And in particular, the boundary CFT is such a quantum field theory. So let me remind you what the Timeslice axiom says. It's a general statement in quantum field theory. It says, in any quantum field theory, any operator that commutes with all local operators at a fixed time must be trivial. And by trivial means it's a C number. And the statement holds for any operator, not just local operators in the theory. So we can apply this statement to a non-local operator as well. Do you mean in the picture here? Are you asking why should I smear the operator of y a little bit? We can smear things a little bit. The rigorous statement is indeed by smearing things a little bit, but the philosophy of this statement is not changing under that smearing. Thank you. Let me give some intuition to what this is really saying. First, let me give an equivalent statement. An equivalent statement of this is that in a quantum field theory, the algebra of operators generated by local operators at a fixed time slice acts irreducibly on the Hilbert space. The two statements are equivalent. And in order to understand why this is true for quantum field theory, well, quantum field theories are complicated. So let's think about a slightly simpler system. Let's discretize quantum field theory by introducing some lattice regularization and think about a chain of spins, okay? So we'll have a number of spins defined on some manifold. Doesn't matter too much whether it's a closed manifold or manifold with boundary. Here I've drawn a one-dimensional closed manifold, but that's not crucial. Once we have a chain of spins, we can consider the set of Pauli operators. In fact, the thing we'll consider is sets of products of Pauli operators. The set is three Pauli operators on each spin together with the identity operator, and we simply tensor it n times, assuming that we have n spins. So this is the analog of the algebra of local operators, because the local operators in this case are simply the identity and Pauli operators. So the statement is that this set of product of Pauli operators form a basis of all operators in the Hilbert space. So this is a basis for all operators on H. For any operator acting on a Hilbert space of n spins, we can decompose that operator in terms of linear combinations of these products of Pauli operators. That should be fairly obvious. And then it follows that any operator commuting with all these products must be proportional to the identity. So in this simplified discrete system, we can prove the Timeslice axiom. Of course, the Timeslice axiom is an axiom, so we're not supposed to be able to prove it in a quantum field theory. So that's why it's called an axiom. But nonetheless, we believe it is true. It is true in all the normal kind of quantum field theories that we encounter, including the n equals 4 super Yang Mills that is dual to ADS. So in a continuum limit, the Timeslice axiom holds. And the moral of that is that this is a basic expression of the local structure of the QFT Hilbert space. It says the local data should be enough to characterize a state in the Hilbert space, in a quantum field theory, that we don't need any additional data. If we had an operator that commutes with all local operators, that operator should be involved in characterizing a state. But we shouldn't have to involve that. Okay, so now applying the Timeslice axiom to the kind of radial commutativity statement that we had earlier, remember that over there, O of y is an arbitrary operator in this arbitrary local operator at any location in the CFT at a fixed time slice. So applying the Timeslice axiom, we find phi of x is a C number. That's clearly incorrect. So this is a puzzle. Any questions for now? Yes?
So if you take your radial commutativity relation, so if you say this is impossible, what's wrong with taking the limit of both sides? Limit r goes to infinity, r to the delta. Then doesn't this just become Ox commutator Oy equals 0, which is okay?
It is okay if the limit point that you are taking is different from y.
It's different from y. So then
If you take a limit where x approaches y, then there could be issues about. But I think the limit is not. You can think about the limit. There could be order of limits issue, here the statement is sharpest if you don't take the limit.
I guess it seems like this Timeslice axiom, what this is really saying is commutator phi x Oy does not equal 0, right?
It's
Because this statement is incorrect. And
That's
then,
correct.
But then if you take the limit on both sides of that not equal to 0 statement, you get something that is true, that Ox comma Oy. Then you would get Ox comma Oy does not equal 0, right? Does that make sense?
Well, the limit could be still 0 if the statement before the limit is not 0. So it is true that knowing phi of x is not a C number means there must be something wrong with our previous statement about radial commutativity there. But that doesn't mean taking the limit, it will still be non-zero. In taking the limit and taking a limit such that x is different from y on the boundary, it becomes a zero commutativity statement in the CFT, just between two different local operators. So, but that doesn't solve the problem we have here. Any other questions? Okay, before I solve this puzzle, I want to sharpen it because it's always good to have a sharp puzzle before solving it. So to sharpen the issue, there actually exists a formula for phi of x in the CFT. Okay, so we first said there's some problem with the commutator. Now we can, in principle, write down a formula and see what happens. And it is a formula in the CFT in terms of a non-local operator. In the CFT. And this follows from the so-called HKRL procedure after Hamilton, Qubit, Lifshitz law. Okay. So let me quickly review that procedure. So the basic idea, let's draw a picture of the box field again, phi of x. The basic idea is that phi of x satisfies an operator equation in the bulk because we know that the bulk theory is governed by some Lagrangian. So the idea is to solve the equation of motion for phi as an operator equation. Let's first consider a free scalar field in the bulk with some mass, and it will we would need to solve the Klein-Gordon equation, and we solve it with boundary condition. Which is the condition, I guess I just erased. Which is the extrapolate dictionary that we wrote down earlier. That when we extrapolate phi to the boundary, we get O. So we should think about this boundary condition as an operator-valued boundary condition and solve the operator-valued equation of motion. That gives us a formula for phi in terms of O in the CFT. So the solution is obviously given by some Green's function. Because this is a linear set of equations. And the Green's function in this problem is normally called a smearing function because it tells us how to smear a local operator in the CFT to get a non-local operator in the CFT. And that non-local operator is what corresponds to a bulk operator, at least in this limit, in this free field limit. So several comments. The first comment is that this is not a standard boundary value problem. In the standard boundary value problem, we set some initial condition, and then we evolve in time. Here, we are setting a boundary condition at radial infinity, and then we evolve radially. And we're doing this with the Lorentzian metric, so that should at least slightly worry us. This is not a standard boundary value problem. And in particular, this means both the existence of the solution and the uniqueness is not guaranteed. Nonetheless, as physicists, we're not deterred by the non-guarantee of uniqueness or existence of solutions. So in special cases, at least, we can find explicit solutions nonetheless, usually because there's a good amount of symmetry to help us. So one such case is in one such special case include the pure ADS case, which has maximal amount of symmetry with negative curvature. So in ADS, if we try to do this, we will find that we can find a K that is supported whose support on the boundary is restricted to all the points that are space-like with respect to the bulk point. So suppose the bulk operator is here, then we only need to involve, in that integral, we only need to use boundary operators that are between these two bands. So this is the region on the boundary that consists of all the points that are space-like with respect to x. Let me call that R, and the support of K on the boundary is restricted to this R. So we can always choose a K, and there's an explicit formula for such a K that can be found by solving these equations in ADS that has this support. This is called the global reconstruction of an operator in ADS. It's global because we are reconstructing an operator in ADS by using all the CFT data that we have everywhere. It's an operator. We will eventually get an operator which is supported everywhere in the CFT. So I'm not going to show an explicit formula for the smearing function in this case. It can be written down. It's not that complicated. So the homework problem would be to find this K. So next, I will talk about a more subtle version of bulk reconstruction. But before that, is there any question at the moment? Okay. So a more subtle reconstruction is that we can actually perform the same kind of reconstruction, but restrict to a subregion on the boundary. So how do we do that? So let's draw another picture, which will be slightly more confusing than that one, but I'll try my best. So this is again ADS, and now we choose a time slice. On top of that, we choose a region, so we break the time slice on the boundary. The boundary time slice is simply a circle. On that circle, we choose a region A, and the rest is a complement. There is a way to define a wedge in the bulk that corresponds to A, So the way to draw this is something like this. And the bulk point is supposed to be inside the wedge. So that's little x over there. So the way to define this wedge, so let me first present the actual statement. The statement is the same operator phi now can be reconstructed on the smaller region. And I'm going to write down what the smaller region is. So we still need to involve a smearing function, but now because we have chosen a specific region A, the smearing function will depend on A. We roughly have the same equation, but now the integral is done on this domain of dependence that we have seen earlier this afternoon for A. The dA it's important that it's the boundary domain of dependence. So in particular, if I look at this picture only on the boundary and turn it 90 degrees, I'm going to find a picture where this is A, and this entire diamond is the domain of dependence. And this equation, which reconstructs the bulk operator for me, works for whenever x is in the so-called causal wedge of A. The causal wedge is what I try to draw here. But if you want to think about it, it is, so this is the causal wedge. It is defined by the causal structure. So it is the intersection of the causal future and the causal past in the bulk of D of A. So this is the bulk causal future, and this is the causal past. What that means is we look at, so there is a boundary diamond on the, that we can, if we turn around and look at a picture from the left, we will see a diamond. And from that diamond, we can look at all the points to the future of that diamond in the bulk that defines the bulk causal future. And we can also define, similarly, a bulk causal past by looking at what points can be connected to this causal diamond by a causal curve in the bulk, and we take the intersection. Those are the points that we can both be reached from D of A and can reach into D of A by a causal curve. So that's the intersection, and that defines the causal wedge. The statement is whenever x is in the causal wedge, we can reconstruct the operator in this way. In the case of pure ADS, and if we choose the region A as a connected region, as we have chosen so far, then the causal wedge of A is also known as the Rindler wedge because it's an ADS version of the Rindler space. So this is called the Rindler reconstruction to be compared with the global reconstruction. So several comments. First, this reconstruction is related to the previous global reconstruction by a Bogoliubov transformation. in the bulk. So from the bulk point of view, there's no difference between these two ways of representing this operator. The second statement is that the Ringler reconstruction is much more powerful and more useful in the sense that we don't need to know the entire CFT data to be able to use it. For example, we might want to use this formula to compute bulk physics, to compute correlation functions in the bulk. Suppose we can calculate anything we want in the CFT, maybe by putting it on a computer. We want to use this formula to compute the bulk quantities. So we are interested, say, in 2-point functions or 3-point functions of phi. We can then plug in this formula and turn it into a CFT calculation. In a global case, we have to really know the full CFT wave function in order to calculate that expectation value of the operators in the CFT. But if we do this using Ringler reconstruction, we only need to use the density matrix of the state on some subregion as opposed to the full wave function in the CFT. Why do I call this a Ringler reconstruction?
Why this Ringler reconstruction is related by Fourier transformation with bulk reconstruction?
This is analogous to the statement that in flat space we can also talk about modes that we define in the global vacuum and modes that we define in the Ringler vacuum. And those two modes, sets of modes, are related by Bogoliubov transformation. Here is exactly the same story, except we're in ADS, not flat space. So let me make a third so before that, I'd like to call this is sometimes called subregion duality. It means that we can construct this causal wedge, at least, by knowing the wave function, the density of state, the density matrix on some subregion in the CFT. So we only need to know some restricted data in the CFT in order to find what happens in the bulk in this region. The third comment is that we can actually simplify the picture quite a bit by looking at just a single time slice. And in fact, that's what we'll do for the rest of the lecture. We'll look at a single time slice. And on this single time slice, so that's the same time slice as that over there in the middle. We have A, and we have A complement. We have some boundary. Turns out the boundary in this case is a geodesic. And we have phi of x. It should supposed to be the same x as in that picture. And the statement is this phi of x can be represented as an operator on A. On the other hand, if we had phi of y over there outside this causal wedge, phi of y cannot be represented in this way on A. So now we can actually use this subregion duality to sharpen our first paradox, radial commutativity paradox. previously, I motivated the statement that phi of x should commute with O of y on the same time slice by appealing to some feeling about how the bulk theory should be causal and therefore local, and therefore space-like separated operators should commute. Now, using Ringler reconstruction, we can make this more precise, because suppose now we can just look at a time slice. Phi of x is here, and O of y is there. We can always represent the operator O of x on a causal wedge that we obtain by just deleting a small region that contains the local operator that we have chosen. So O of y is an arbitrary operator, local operator in the CFT, but as long as we have a chosen location, we can choose to look at how phi of x is represented on this complement region. The reasoning for that is that the complement region has a very big causal wedge that surely contains the center operator in the center. So then phi of x represented in that way is really a CFT operator that has space-like separation with respect to O of y, and therefore they commute. So before I solve this puzzle, let me introduce another one, which will be quite motivating for us eventually. I call this the ABC puzzle. So the ABC puzzle is, in some sense, a different aspect of this, but it's good to still have it. So the idea is to divide the boundary into 3 equal regions, A, B, and C. And the operator at the center is, again, phi. This is, again, a single time slice. And I've joined 3 geodesics corresponding to these 3 regions. So the first statement, phi cannot be represented on either A or B or C. That should be fairly obvious because the causal wedge for A is in here, very small. The causal wedge for B is over there, and none of them contains the operator at the center. The second statement is phi can be represented on the union of any two of the 3 regions. So union of A with B, union of B with C, or union of C with A. This is because if we take the union of A and B, it's a fairly big region, and the causal wedge is this entire region that contains the center. So according to the rules that we discussed, phi should have a representation on that region, on that boundary region, and we can call this. So there exist at least 3 representations of phi. We can call them phi AB, phi BC, and phi CA. Now the issue is that they cannot be the same operator in the CFT. They don't even have the same mutual overlap. The mutual overlap between these 3 regions is, roughly speaking, the empty set. So they cannot possibly be the same operator in the CFT. And this is the puzzle. How are we supposed to think about the equation up there if we find different ways of applying that equation gives different operators? And even more seriously, this begs the question of where is the information that characterize the operator at the center in the CFT? Where is it located in the CFT? This could be a spin that we want to measure in an experiment, and maybe we have access to the CFT. We should be able to know what to do. So it turns out that these puzzles have a very nice solution, but before I go on, are there any questions at the moment? Yes.
Is there any restrictions as to when the subregion duality holds? For example, we're always talking about the boundary being element space being broken up into tensor product factorized into like A and A complement. And also, does it hold for any? Does it only hold for pure ADS or any asymptotic ADS geometry? Like, does anything interesting happen if you consider a large black hole?
Before even talking about black holes, we can talk about excitations of ADS that does not even involve black holes. Maybe just for simplicity, let's talk about that. Or maybe another generalization is we can talk about regions A which are not as simple as this. For example, we can talk about regions that consist of unions of disconnected subregions or have weird shapes in higher dimensions. So all these are not needed right now for the argument. For the argument, I want to be as simple as possible, so I've chosen a pure ADS and single interval. But eventually, after we realize, go through this story, we will eventually be able to derive a theorem that says, in all these cases, there is a version of a very fairly powerful statement of subregion duality that tells us what exactly is the bulk region that is dual to, in this sense, dual to the boundary region, for any boundary region and for any state. And the answer will be something called entanglement wedge, but that will not be needed right now. Any other questions? Okay, so these puzzles can be solved by interpreting ADS-CFT as a quantum error-correcting code. If you don't know what a quantum error-correcting code is, don't worry, I'll give you an example. But generally speaking, this is a device that we use to protect quantum information from decoherence or other kinds of errors. It's designed to encode quantum information into the non-local structure of entanglement between many degrees of freedom, and therefore, because it's non-locally encoded, any local error will have a small chance of corrupting that information. So those are the general statements. Let me give a concrete example. Turns out the most instructive example is a quantum error correcting code that I will call a 3-qubit code. So a qubit is simply a 3-dimensional analog of a qubit. So it's a 3-dimensional Hilbert space characterized by 3 states. We can call that 0, 1, 2. You can think about a spin 1 photon and its spin, photon is not a good idea. Let's think about spin 1 massive particle. And that's a qubit. So we can engineer these kind of things in the lab And say we want to have Alice send a single qubit to Bob. And the state that she wants to send is a general state of a qubit. So general superposition of the basis states. If the world is classical, then things would be very simple. Alice would try to make many, many copies of the same state and send them over. As long as a majority of them gets to Bob correctly, then Bob will be able to figure out what it is. But we're in a quantum world, and we have a no cloning theorem that prevents us from doing this. Still, we would like to we want to send it so that we want to be able to send the information reliably, accounting for the fact that sending something by mail is never reliable and can get lost or corrupted. So the idea is to encode the state into a 3-qubit state. So instead of sending 1 qubit, Alice is going to send 3 qubits instead. And the state that she wants to send is abstractly the same superposition of 3 qubit states, but special ones. So this K tilde is supposed to mean some special 3 qubit state that we can engineer beforehand, and for any state of the 1 qubit that she originally wanted to send, she can instead send this new 3 qubit state. So let's be a little bit more concrete. Let me see how am I doing with time. Okay. So let's be a little bit more concrete. So K tilde is supposed to give a basis for a 3-dimensional subspace in the 27-dimensional Hilbert space of the 3 qubits. Each qubit has 3-dimensional Hilbert space. 3 qubits is a 27-dimensional Hilbert space. So K tilde is a very small subspace inside that 27-dimensional Hilbert space. And this is sometimes called the code subspace. And we can write this down explicitly. So the 0 tilde state is simply a combination of 0, 0, 0, 1, 1, 1, 2, 2, 2. And the 1 tilde state is slightly different combination and the same goes for 2 tilde. So these equations give the exact way of how Alice should encode the single qubit state that she originally wanted to send into the 3 qubits. She simply follows through this map. And also some terminology, we usually call the qubit that she originally wanted to send the logical qubit. So this problem has 1 logical qubit. but now she's encoding it into 3 physical qubits. The physical qubits are what are being sent. The logical qubit is the information that she wanted to send. So a few features of this map. So first, this H code is symmetric between the exchange of all the 3 qubits. None of the qubits is privileged under this map. They are on roughly the equal footing. Second statement is any state in the code subspace is highly entangled. To see that it's highly entangled, we can look at the density matrix on any one qubit. So if we take any of the states, including any superposition of the states that we wrote down, and trace out 2 of the 3 qubits, doesn't depend on which 2, you can choose any 2, we will find the density matrix for the remaining qubit, and it's always maximally mixed. What this means is that any one qubit, any one physical qubit has 0 information about the state that Alice wanted to send. Because the state is maximally mixed and independent of what the underlying encoded message is, there's nothing someone peeping into the state just by looking at one of the 3 qubits, they cannot get anything out of it. This is the feature that leads to the remarkable property that any 2 out of the 3 qubits contain the complete information of the physical state, of the logical state that Alice wanted to send. What that means is that if we take any 2 qubits out of the 3, we can completely recover the information, the original state that Alice sends. So even if Bob loses one of the 3 qubits, that's going to be okay. So in order to see that, we can define the so-called decoding operators. So we can define a unitary operator U12. U12 really means it acts on the first and second qubit. And it can act in some particular ways by permuting all the basis state. So this is just one way of writing down what a unitary operator is. So if we define such a unitary operator acting on 2 qubits, we can show easily that acting the operator on the first 2 qubits, and if we acted on any of the basis state that we defined over there, we will be getting the corresponding logical information back on the first qubit, so k back on the first qubit, times some state chi acting some state chi on the last 2 qubits. And the chi state is simply the maximally entangled state on the last two qubits. It's not super important what chi is. The important thing is chi does not depend on k. So another homework problem is to check this. And from this, we can immediately recover any state that Alice sends by using the U12 operator. Just by making a pseudo linear combination of the previous formula. So by symmetry, we also have U23, U31 doing the same job, also decoding the information for us. So this is the feature of a quantum error correcting code. We can decode the information even if we have lost some part of the system. Maybe it gets corrupted. And we can lose any one of the three qubits as long as we know we have lost which one, and then we can reconstruct the information by acting the appropriate unitary transformation on the remaining two qubits. So this is very, very similar to the ABC puzzle that we had earlier. There's a slight difference, which is here we're talking about decoding the information. There we were talking about acting on the state in some particular way using a bulk operator. But that can easily be remedied. So I think I'm run out of time, so I'll save that for the next lecture.
Questions?
If you have a bulk operator that lays exactly at the boundary of the causal wedge, you reconstruct it? Or do you need to be epsilon inside? Like if it's in the center and I give you exactly half, is that okay, or do you need half plus epsilon?
I think it may depend on how you define the operator and what it means to say that it's exactly on that surface. Also, it may depend on what operators we're talking about. Whether it's, for example, it could be different for different operators. It could be for a metric operator, maybe you can construct it. For the canonical momentum operator, conjugate to it, maybe you cannot. But I don't know the full answer.
Yeah, so the bulk theory is a gauge theory, so you expect that you need to dress like local fields to the boundary with some Wilson lines to make them gauge invariant. Is this ABC puzzle different than like choosing to which region do I?
Very good question. So up to now, I have said nothing about gauge invariance in the bulk. And indeed, without the diffeomorphism invariance really tells us there is no way of strictly talking about local operators in the bulk. What we can do, well, here what I'm doing is to work at leading order in the 1/n expansion, where we can ignore possible issues related to the dressing of this operator. But we can also include the dressing of the operator to account for the diffeomorphism invariance. And what amounts to is to, for every operator phi in the bulk that I'm talking about, I have to include some gravitational analog of the Wilson line. And so I've talked about two puzzles, the radial commutativity puzzle and the ABC puzzle, and both of them can be phrased with the gravitational dressing taking into account. But that's way more complicated than what I've presented. And a leading order in 1 over n, we don't need to worry about that.
But the puzzle still exists with
The
addressing.
puzzle still exists. For example, in the radial commutivity puzzle, I derived from the zero commutator statement and combined with a Timeslice axiom that the bulk operator should be a C number. So that's totally ridiculous. If we included a gravitational Wilson line ending at some boundary point, so connecting to the bulk, from the bulk point to the boundary point, then we would, using the same sort of argument and a slightly stronger version of the Timeslice axiom, I think called Hart duality, we would conclude that the bulk operator phi of x is a local operator at that location, at the endpoint of the Wilson line. And that's equally, perhaps a little bit less, but equally ridiculous.
Thanks.
How does this kind of error correcting code scale when Alice wants to write very large entangled messages? Like there are 100,000 bits or something, qubits, which are all entangled, and Alice wants to send such an entangled state. I mean, I can imagine that this is the simplest case. She has 3 states entangled, but no other states are interfering. But I think in complicated quantum computations, the entanglement is much, much larger. And the question, my general question always is, how does this scale when the number of qubits increases?
So tomorrow I will be giving more complicated examples. So these are very, very coarse-grained toy models that has only 1 qubit or qubits worth of information. Tomorrow I'll present more complicated examples based on tensor networks that have more information. And then you could be asking a question whether, so there are 2 questions. One is what happens when the number of logical qubits is large, but does not scale with, let's say, n squared in a holographic setting. For example, it's a fixed number that is much larger than 1, like a 1,000. And another sort of question is what happens when you try to scale it up as n squared as you take the large n limit. So in the first setting, there is nothing wrong with just coming up with 100 qubits encoded in this setting by using more complicated version of this. In the second case, what you, as I will discuss, what will happen is you will encounter black holes, and the correctability of the code will decrease as you include that amount of, as you try to incorporate that amount of information in the region, in the bulk. So that's in agreement with our intuition that trying to measure things, a lot of things in a small region in the theory of gravity will create a black hole. But there are ways of seeing that very explicitly in these sort of models and the tensor network models.
This thing, see again.